In this video, I'm going to show how to build the character table for the C6H point group. And so C6H is not actually a very common point group in chemistry or things like that. But the reason I chose it is because for one, it's a big table, and so I wanted to show kind of how building a larger table than the C2V and C3V looked. The second is that it has the G and U subscripts in it, and so this gives me kind of an opportunity to explain that. And the third is that it has complex exponentials in the table, and so it would give me a chance to kind of explain what that is. And so in this video, well, I'm going to go kind of fast through the table building because it's very long and it would be probably kind of tedious to listen to me go through it in the minute detail, but I do have it all written down on here, and this whole thing will be linked to in the description down below if you wanted to look at it in a little bit more detail. And so the way that I did it is I approached it kind of like a logic puzzle, because that's what it is, where you're sort of trying to eliminate different things from the possibilities, and so you can narrow it down to particular irreducible representations. I've never seen or read or you know experienced anybody actually deriving this table, and so the way I did it, for all I know, is a much longer and complex way than it should be done, or maybe it's an overly simplified way that is not sort of the most rigorous way. So I don't know, but I do. It did help that I know what the answer is. I know what the table for C6H is supposed to be, and so that sort of helped guide my thinking as I went through this. But other than that, all of this is going to be sort of my thought process on the thing, and so I guess this is the Thomas Harper version of how to derive the C6H character table. All right, so with all that out of the way, let's start here. So first we want to get our matrix representations, our 3x3 matrix representations for the C6H, and this should actually be a 6 right there. And so we're using this right here where we are doing a rotation around the z-axis, and then this is plus or minus 1 because we will have inversions on here. And so these are the matrix representations for this C6H point group. So we have our identity, we have our rotations here, we have our sigma h, we have our inversion, and we have our S operations here. And so again, we will block diagonalize in the way that we did for the C3V, where we have a 2x2 for the X and Y, and then a 1x1 for the Z here. And so I have that all like this, and I have it color coded. So that gives us the following table, which has these two irreducible representations, which based on what we know about tables from the last couple videos, we know that this is incomplete because we should have 12 irreducible representations and we only have 2. And so now comes the sort of logic puzzle part of all of this. We have to use what we know about tables, basically the sort of orthogonality rule, essentially, in order to fill out the rest of this table. And so the first thing we know is that we always have a totally symmetric representation. So we can put this one with all ones in here first. And we know that that the orthogonality means that if we take the sum of all the pointwise products here, that it should be equal to 0. And so we can deduce, since there are 12 classes, combinations with the 6 plus and 6 minus will work when paired with the totally symmetric representation. And so we have the totally symmetric representation here. And so if this is to work, then half of these have to be minus and half of them have to be positive. And so we can then take the orthogonality relationship with the purple one up here and with this sort of, I guess, wheat colored one up here, which are A and E. And so I put A and E here because we know that these have to be A because, so this B column here, I've just replaced the C6, and that is our principal axis. And so these are both positive with that. And so those are A. And then this is an E because it has these 2's in it here because of the 2 by 2 matrix representations. All right, and so then we get these relationships here. And so the first one tells us, like I said, that we have to have the balance of positive and negative, and the other equations only satisfy this if we have these relations here. And so from that we can sort of derive all these relations, sort of, using the logic puzzle of it all. And so we get these relations. And so we end up with these three things down here, though. This A equals D equals 1, or A equals G equals 1, or A equals J equals 1. And so we have to satisfy these that I have in the sort of the multicolors up here, and sort of test for all three of these ones here. And so that gives us these following candidates. So these candidates satisfy all these conditions up here. And so then I have the A equals G, A equals D, A equals J for each of these. And so now we will test each of these in this table against one of the representations that we already know. And so I'll use this purple A one here, which is positive 1 for the first 6 and then negative 1 for the second 6. And so I go through and do the orthogonality with each one. So this first one up here, so I'm just doing it in order that I have on this table. This B with A equals G is orthogonal. Then we have a bunch of non-orthogonal. Then this last one here is orthogonal. So this A with A equals G, or A equals J here, is also orthogonal. And so we have two orthogonal ones that we found from there. So now we test against the E here for orthogonality. And we find that just the first one is orthogonal with that, and the second one is not orthogonal with that. And so we accept this one here, the B where A equals G here. And so we can add this one to our table. And so we get this table right here. So now we have these four relationships here. So we can look for another one, and we kind of go through the same thing as above. So we look at the orthogonality relationships with our new B here and with our purple A here, and we get these conditions right here. We get this another thing here with a bunch of the, A equals D equals 1, or A equals G equals 1, or A equals J equals 1. And so we would just go through the same process as we did up in here, but I'm not going to show that here because it's kind of it's just long, and it's basically the same thing. And so we will end up with a representation that looks like this. So this B here in the brown, and so we can make this the following table here out of it. And if we look at it with our symmetry operators put back in for these A through L here, we get a table that looks like this. So you'll notice I put these subscript G's and subscripts U's here. For now, just know that G means that it is symmetric with inversion. So these two numbers here, the G subscripts mean it's symmetric with that. The U mean it is anti-symmetric with that. And so I'll talk a little bit more about that later. So we still don't have enough irreducible representations. So we have 5 of them here, and we need 12 if we want it to equal the number of classes up there. And so we can keep looking. So the operation of the diagonal matrices are the ones that have 2's in their columns. So we're going to look for ones that have that are E-type representations here. And so we will use this orthogonality relationship again. So if we use our known E and search for unknown E's, so we're doing this, and we know that the first one is always going to be positive, so we can put a positive 2 there. So we get this relationship here, so we have this equal to this side here. So we have 6 unknowns on the left, which I have in the blue here. The things with the 2's I have in kind of that dark red here. And then we have 6 unknowns on the right. And we know that to be orthogonal with the totally symmetric representation, we have to have this. And so it must be that the negatives and positives balance out. And so knowing that A equals plus 2, we can narrow it down to these 4 situations here. So this top one here is the one we already know just from the matrices, just from taking the character of the matrices. This one is solved because we know we have to satisfy this, and if we have everything equaling to positive 2, then all of the ones have to be negative 1. And so then we can have j equals minus 2 in both, and then we can switch between the d and g being 2 and minus 2. And so we get a table that looks like this, where these first 2 rows up here are the ones that we know and the one that we can just sort of easily solve from that. But now these second 2 rows down here are things we have to look at in more detail. So we need to determine which of the ones in the last 2 rows is positive or negative. So I put plus or minus in each of those. And since in both cases we have plus 2 and minus 2 on either side, we get something like this. And so we know that the b plus f plus I plus k has to equal to c plus e plus h plus l. So we still have to figure out whether there are sort of, 3, 2, or 1 minuses on either side. So we can use the orthogonality property to show that if we have our E3 and E4 go to these here, that what we have ultimately is that if we have the C3 times C4, E3 times E4, H3 times H4, L3 times H4, and then minus all these blue ones, it has to be equal to 8. And this tells us that the B3 and B4, F3, F4, I3, I4, K3, and K4 have to be opposite signs of each other because we're subtracting here. And so these terms here each have to become negative in order for this to be positive, in order for us to get it equal to 8. And so if we use the orthogonality property with one of our B representations, so the one with the alternating signs, we get this relationship right here. Then we look at it with the purple A, which is the first half plus, second half minus. We get this relationship right here, and these can only be satisfied if B equals C equals E equals F equals minus 1. So we know that this representation must be equal to this, and since we know that the B, F, I, and K have to be opposite in our other one, that the C, E, H, and L have to be the same, we can just infer from this one here, this one down here. And so this gives us all 4 of our E representations here. And so we can put it back in the table with these E rows kind of moved around, so in the way that I already know that they're supposed to be. And so some things to notice. So first, we have the principal axis C6 here, to which the groups are either symmetric or anti-symmetric, and so that's where we get our A, B here. And we don't have any C2 axes perpendicular to this, nor do we have any vertical mirror planes. And so we won't have any number subscripts on our A's and B's here, because the numbers are referring to the C2 or the reflection planes, the perpendicular C2s or the reflection planes. What we do have, however, is the inversion, as I said. And so the G means gerade, and the U means ungerade, which are German for even and odd respectively. And so G just means that it is symmetric with inversion, and the U means that it is anti-symmetric with inversion. And so we can actually put these on our E representations here as well. And those ones we will number just to sort of differentiate them from each other. And so we can see that this table agrees with this one below that I took from this book, Symmetry, Group Theory, and the Physical Properties of Crystals by Richard C. Powell. So we see that it agrees with that. And so does that mean we're done? Well, not exactly. So what we see here is we only have 8 irreducible representations, but we have 12 different classes up here. So we're still missing 4 classes. So this is achieved by splitting the E row representations into sums of complex conjugates. And so 2 is equal to 1 plus 0i plus 1 minus 0i. So the i's just cancel out because of the zeros, and we get 2. 1 equals half plus IB plus half minus IB. Minus half equals minus half plus IB plus minus half minus IB. Where in both of these cases, the plus IB and minus IB will cancel each other out. All right, so we can use these complex exponentials here, which, if you remember, the Euler relationship is the cosine of x plus the I sine of x. And so our x here is equal to k times 2 pi over n. And so if we have k just equal 1, it's 2 pi over 6, which simplifies to pi over 3. And so we have our I pi over 3, our I minus pi over 3, or minus I pi over 3, and minus negative I pi over 3. And so it gives us the 1 half plus square root of 3 over 2, and the 1 half minus square root of 3 over 2, minus 1 half minus square root of 3 over 2, minus 1 half plus square root of 3 over 2. And so if we do these additions and subtractions, so we can get a 1 from adding this e to the I pi over 3 plus e to the negative I pi over 3, and minus 1 we can set equal to minus I pi over 3 minus negative I pi over 3. And then our 2's obviously just from above. And so the reason this works, as you may have noticed here, I have these 6 roots of unity here. And what you'll notice is that this figure here is a hexagon, and it therefore has a rotation of C6, as well as an S6 symmetry, where you could move from here to here, which is just a C6 rotation, or you can move from here to here and then do a reflection through the plane of your screen, which would be an S6 rotation. And so we see that when we put these in the complex into complex numbers, then we essentially just have our shape here, our symmetry, but in the complex plane. And so that is what those complex numbers mean. And so I put these down here just to show that the numbers that are on this figure here, the e to the pi, I pi over 3, e to the 2 pi over 3, e to the 4 pi over 3, and e to the 5 pi over 3, does give us our pluses and minus for half and square root of 3 over 2. And so, like I said, this figure here, well, I mean, if we were just looking at the pure figure, it probably wouldn't be C6H, but we can see how a C6H would fit into a figure that looks like this in the complex plane. And so when we do that, we get a table that looks like this right here. And so we see our E's, we have all these split, so the 1's here and the minus 1's and 1's here, where I could have put the plus and minus I0 on each of these, but since the imaginary part just goes to 0, I suppressed that. But we can see in the C, in the rotation columns here and in the S columns here, we get these complex exponentials, which correspond to rotations and inversions and so forth in the complex plane. And so that is sort of what those complex numbers mean. And so we now have our 12 irreducible representations. It's with this version that we can get the addition of each of the squares here. And so for these complex numbers here, I've just multiplied by the complex conjugates in each case, but it still just gives us 1, and so we get our h equals 1 plus 1 12 times up to 12, and so we get our h equals 12, and so that's what we wanted to get. But in practice, we usually just use the real numbered version because we like to work with real numbers when we're thinking about things in real space. And so, this table we see here is something you would often find in a book. And so, like I said, I got this out of this book up here, the Symmetry, Group Theory, and the Physical Properties of Crystals. But one of my inorganic chemistry textbooks actually has it in this version here, which is kind of how I knew what the answer was supposed to be, but I just copied this out of my inorganic chemistry textbook. So you'll see it in both ways, with either the sort of complexified version or in the real number version. And so you see this has these star superscripts by the e's, which are for a footnote, essentially, that says that those can be split into complex numbers. And so the other thing to notice, we have this on tacked on here again, which tells us how these functions transform under these different operations here. And so this is actually a molecule that exhibits C6H symmetry here. And so like I said, this is C6H is not a very common one for molecules, and so it actually took a little bit of looking for me to find one that satisfies this. But we can see we have these in blue, these nitrogens here, and then we have these methyls coming off of it, which can be sort of tilted so that it's more like a fan blade, which makes it so we don't have those C2 perpendicular axes or any vertical mirror planes. And so this molecule satisfies that. So we can put our coordinates like this. So we're sort of looking down the z-axis. We have the x going this way and the y going that way. And so we see if we do these C6 rotations, so we start here, we do a C6, a C6, 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 where 2 C6s is the same as a C3, 3 C6s is the same as a C2. Then we have sort of a C3 squared here, or to the 5th rather, and then the C6 to the 5th there. Yeah, that would be C3 squared, not C3 to the 5th. We see that when x equals plus, then y equals plus, and when x equals minus, y equals minus. Furthermore, we see that the transformation into combinations of each other, and so this will be x and y. So we see when we go to this, for instance, x now has an x and a y component. The y has a y and an x component, and so they become dependent on each other. So we see that they transform like each other under rotation. So the C6 has x go to positive x and y go to positive y. The C6 to the 5th and, has x and y go to positive. The other ones are negative. So we can look up at our table here, and so we can discern that it must be, I mean, we can already see what the answer is here, but we can see that it must be either the E1U or the E1G, because we have that the C6 has to be positive, the C3, C2, and C3 squared all have to be negative, and the C6 to the 5th has to be positive. And both the E1G and the E1U satisfy that. But then we have to look at the fact that that under an inversion, this is anti-symmetric under inversion, where I can be equal to S2. And so if we do an inversion, we have our y equals plus, x equals plus. We invert, the x sort of moves over to this side, the y moves down here, and they both become negative. And so S2 on x gives us minus x, S2 on y gives us minus y. So it's anti-symmetric to inversion, and therefore must be the E1U. But anyway, that was everything I wanted to talk about for this. The main things I wanted to talk about were sort of these G and U subscripts and what these complex numbers in here mean. And so the thing to remember is that even in these ones that don't show the complex number, those are complex numbers. It's just that the complex part has gone to 0. So that would be this point here and this point here in the complex plane where we see it has 0 and 0 complex part. But yeah, that is the C6H table. And so that is going to be the last sort of, table that I sort of, spend an entire video talking about. In the next few videos, I'm going to talk about sort of these tables, or at least like the irreducible representations and things like that a little bit more generally. But anyway, I think knowing what these tables mean will help to understand the sort of generalization of these processes. And so I thought it was important and maybe even hopefully interesting to go through a few of these tables and talk about them in some detail just to get us oriented about what each of these things mean. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.